Latitude Media, covering the new frontiers of the energy transition.
I'm Shail Khan, and this is Catalyst.
So we do a very brief electrical inspection, something like 5 minutes, and we literally wheel it out to the field where we have a spot for it and plug it in.
Coming up, second life batteries get reincarnated, so to speak.
Need to accelerate procurement for an upcoming solar or storage project? ANSA is your best source of intel to stay on top of current policy, tariff, domestic content, and supply chain issues. ANSA's team of experts is available to help you adjust procurement strategies, secure safe harbor products, and find existing inventory in the U.S. as policy continues to evolve. Learn more about ANSA's subscription and service options to help you navigate an uncertain market at go.ansarenewables.com/latitude.
Imagine a world where connected devices like EVs, home batteries, and smart thermostats work together to support a more efficient, reliable, and affordable power grid. Energy Hub is making this vision a reality today. With Energy Hub's Edge DERMS platform, utilities can create virtual power plants through customer-centric flexibility programs, making it easy to manage distributed resources and balance the grid. Unlock grid flexibility and reliability through cross-DER management with Energy Hub, the trusted Edge DERMS leader. Visit energyhub.com to learn more. Catalyst is brought to you by Antenna Group, the communications and marketing partner for mission-driven organizations developing and adopting climate solutions. Their team of experts help businesses like yours identify, refine, and amplify your authentic climate story. With over 3 decades of experience as a growth partner to the most consequential brands in the industry, their team is ready to make an impact on day one. Get started today at antennagroup.com.
I'm Shail Khan. I invest in early stage companies at Energy Impact Partners. Welcome. Okay, so as I'm sure Catalyst listeners know, end-of-life batteries, particularly those coming from electric vehicles, are not really end-of-life. Batteries don't usually fail, they just degrade over time. And so when the battery reaches the end of its useful life in a vehicle or in something else, it's still got a lot of value. But the question is, what is the highest and best use of it at that point? One option is refurbishment and putting it back in a vehicle or its original application, which makes sense in some very limited cases, but not usually. So that leaves 2 other options. One, you recycle the battery for materials and minerals. And the second is you repurpose the battery, usually as a stationary energy storage asset on the grid. There's an economic calculus to the decision between these two that has a bunch of variables: the current value of the materials themselves, the actual processing technology, the cost of new stationary batteries, etc. And you might think that there's a right answer, and indeed many people do. And generally, historically, that right answer has been recycling for materials. But that's why I found it interesting when Redwood Materials, which is the company founded by Tesla founder J.B. Straubel and best known as a battery materials recycler, announced a new division called Redwood Energy, where they're focused on stationary storage. So that means they're going to take in end-of-life batteries and send them into one of 2 streams, either materials recycling or repurposing for grid energy storage assets. So what underlies that decision tree, and what is it that unlocked the possibility of an economic second life battery on the grid? Well, who better to answer that than Colin Campbell, himself a longtime Tesla veteran, but now the CTO at Redwood. Also, before we begin, I'm hosting another Ask Me Anything episode where I answer your questions, big and small, about climate tech, the energy transition, investing, et cetera, et cetera. Just email us if you want to ask a question. Thank you to all of you who have already submitted many great questions. We have room for more, so hit us at catalyst@latitudemedia.com. That's catalyst@latitudemedia.com. And for now, here's Colin. Colin, welcome.
Shail, it's a pleasure to be here.
Excited to finally have you on and to talk about what to do with end-of-life batteries, the various things that you can do with them. Maybe start by talking to me about, from just a technical standpoint, like you get a end-of-life battery. I guess you tell me, it probably varies based on the type of battery and the application, but I don't know, take an EV battery, for example. Like, what state is it in when it rolls up into your factory? And what are the technical parameters that you're looking at to determine its condition?
Yeah, I think the state of the batteries that we received, the old electric vehicle batteries, it's better than you might think. Those things are incredibly highly engineered, durable objects. So from a physical perspective, they're usually almost new. And then from an electrical and electrochemical perspective, we receive them when a customer might get frustrated with them, typically. So that's something like, I've lost 20% of my range, or the acceleration isn't what it used to be. Something like 20% increase in impedance, 20% decrease in capacity is typical for what we see.
And then how different is it if it's not an EV battery? Like if you're taking, I don't know, consumer products, batteries and things like that? Because I know you guys get a pretty wide variety of streams incoming.
It's a real fantasy land if you're a battery nerd to look at the stream of things that we get. It's literally everything under the sun. Ear pods, toothbrushes, power banks, and those, they're so varied. There's so many of them, and they're so difficult to reintegrate into a Second Life system. That's not something that we've looked at very closely, to be honest.
Okay, so as we talk about Second Life, predominantly right now we are talking about EV batteries.
Yeah, that's right.
Okay, and then I guess let's talk about chemistries for a second. Presumably, what you're getting, if it's an end-of-life EV battery, these are NMC chemistries that are coming in mostly?
Today, they're predominantly NMC. You could think of it as what we get is what was built roughly 10 years ago. So we're time shifted from the manufacturing trends. Right.
Okay. And then so here's the core thing I think is interesting and I want to understand, right? Like, so at Redwood, you've been taking in all these end-of-life batteries for a few years of various kinds, but including the EV batteries, and historically, mostly recycling them for the material value. Now you are doing that sometimes, but sometimes refurbishing them and turning them into stationary storage assets. So talk to me at the high level through the calculus. Like, you get an end-of-life battery that comes in the door. What determines which path makes sense?
Yeah, we do a pretty brief inspection. So there's a mechanical one, and then there's an electrical one to check the health of the pack. So things like cell balance, impedance, are all of the internal electronics still functioning, and reporting out very detailed diagnostic data about the pack. And what we found is that if all of those lights are green, 95% of the time, the pack is going to be usable for grid scale energy storage. So it's a pretty brief inspection, honestly.
So there's the question of, I guess what you're answering right now is, can you use it for grid scale energy storage? But the other question is, should you? Right. And that is an economic question, I guess partially a technical question, because in either case you have work to do. You can't just like put the battery back out in the field, and you can't it's not automatically recycled into materials. So how do you think about the economic question, I guess, of which makes more sense to do?
When you think about the economic value of these packs, they don't need to have as much life left in them as you might think in order to make sense to put back on the grid. So since we have developed a really low-cost, hot swappable way of putting the packs in, the cost of integrating the packs to the grid itself is really low, the install cost, the swap cost. And so the amount of usable life that's left in a pack doesn't need to be that high in order for it to really be valuable and economically profitable to put back on the grid, given the value of the grid services that these storage sites are providing.
I guess the one of the questions that I imagine is embedded in there is, okay, so in one path, which is the one that you've done more of historically, you break the battery down and you get a bunch of useful materials out of it. You get the cathode active, or you reproduce cathode active material, you get the anode material, and so on. And so there, the value you're able to derive from your end-of-life battery is a function of the price you can yield in the market for those materials minus your reprocessing cost, presumably. In the other context, it is how much value is there on the grid for doing the stationary storage asset minus, again, your sort of refurbishment cost, and you're competing against different things. In one case, you're competing against like new cathode active material. In the other case, you're competing against new, let's say, LFP packs, right? And which is outside the US has been a falling knife of a cost, but in the US is a little more complicated because of tariffs and various things. But to a first order, like from a first principles perspective, all else equal, would you rather just refurbish the battery to put it on the grid than to break it down to its constituent materials? Is that the right way to think about it? And you should only do the latter thing if either the battery is incapable of being put up back on the grid because it doesn't work in one way or another, or because we're in a market where like CAM prices have spiked or something?
Yeah. We don't have to choose, right? So we typically will do both. We will send a battery out to a grid scale energy storage site to provide grid services when that is economically sensible, which is 95% of the time. And then we will go on to recover the metals value from it. So it's additive. We think of it as a detour. We can put these batteries out to a grid storage pasture for a little while to really extract all of the energy storage and power delivery value that they have, and then go on to recover the critical minerals from them and regenerate fresh cathode materials.
That gets to another question, I guess, which is how much of a useful life do you expect there to be for the grid storage asset? You've already had a 10-year useful life as in an EV. It's down to 80% capacity or something like that. Now you stick it on the grid. Is it another 10-year useful life? Is it less? Is it more?
The life of the second life battery on the grid it's certainly long enough to be economically valuable. And that in order to make economic sense, it's really 1 or 2 years, hundreds of cycles, low hundreds of cycles.
So for that to be true, it must be remarkably cheap to deploy, right? Because you're up against a new LFP project, let's say, energy storage project, where I don't know what the current price is, like fully delivered, but like a couple $100 a kilowatt hour, probably something like that. But that has a 10-year life, or 10-year warranty life anyway. And so presumably what you're saying is that, look, take an end-of-life NMC battery, you get it very, very cheap, if not free, and then you have some cost you bear in which I want to talk in a second about like what you actually have to do to it, but you have some cost that you bear in turning it back into an asset you could put on the grid. That cost must be so low that the total installed cost of the second life ESS battery is like significantly below the cost of a new de novo LFP battery today.
Yeah, I mean, you've nailed it. I was, to be honest, always a little skeptical about second life energy storage as a thing in the world. I was like, how can this possibly compete with a purpose-built product that's really optimized for the application? And I think it's only started to make sense in the last year from the volume of packs that are coming back. And then the other thing is we have put together, like you said, a really simple, straightforward, low-cost way of integrating these packs that were originally designed for another purpose back into the grid. And doing that very simply, very cheaply is central to doing this well, I think.
All right, so walk me through that process. So you get an end-of-life NMC battery off of an electric vehicle. What do you have to do to it?
So we do a very brief electrical inspection, something like 5 minutes, cell balance, impedance check, and we literally wheel it out to the field where we have a spot for it and plug it in. So we are not opening up the packs. We are not removing the modules. We are really using them as they were installed in the car. You can think of it really as a giant parking lot for electric vehicles, except there's no wheels. It's just the packs and the power electronics that went with it.
Wait, so where's the innovation? I mean, that makes it sound like literally anybody could just take an end-of-life pack and plug it into the grid and be done. What's new here? What did you have to do?
You need to be really thoughtful about the high power electronics design to integrate an incredibly wide variety of packs, to talk to an incredibly wide variety of packs. to sensibly dispatch each one of them as part of an integrated energy storage asset to optimize their value. The mechanical design of the site itself to keep it low cost is not that straightforward. And these are all things that we think we've done really well.
So it's power electronics and software, basically. Like to a first order from a physical standpoint, you're just plugging a bunch of disparate batteries into one system to make it operate like a single cohesive grid scale energy storage asset. There's some magic in the combination,
power
the
conversion,
optimization, the power
software,
conversion.
exactly, coordination, all of those things. Also, it's not that simple to collect a whole bunch of packs like this. So this business is one that really makes a ton of sense at Redwood, where we are already collecting north of 80% of the end-of-life EV packs across the nation. That's not a small feat to have the feedstock available. It's really heterogeneous. It comes from a million different places.
Right. Yeah. I mean, just having the feedstock is clearly a big advantage for you there. I mean, maybe that gets to this next question, which is how much of this can we expect? I mean, battery recycling in general has always been this interesting game of, like, as you said, you're 10 years behind, at least with EV batteries. And so we're today recycling the volume that we deployed 10 years ago. And so I feel like, I mean, you probably know the EV adoption curve a little better than I do, but it feels like the sort of inflection came less than 10 years ago, like somewhere in between. So like the real ramp in volume of end-of-life batteries you would have available to do this with seems like it's coming sometime in the next 5 years or something like that. So how much volume do we see now? How much volume might we see? And like, if you step back, how big a player in the ESS game do you think this can and should become?
Those are exactly the right questions to ask. The future is preordained here, right? These packs were manufactured a decade ago. We know we can predict how much energy is going to be available for this and at what time. So today, it's on the order of 5 gigawatt hours a year that's coming off the road.
Globally or in the US?
US.
US, 5 gigawatt hours. Okay.
And it's on the order of 150 gigawatt hours a year new EV production that's going into service. And then I think the battery energy storage that was deployed in the US last year was on the order of 50 gigawatt hours. So already coming off the road today is a tenth of what's being deployed.
Is that 5 gigawatt hours rated, right? Or is that 5 gigawatt hours available?
Great questions. That would be the
it's rated probably.
Brand new capacity. So even though if you discount it by, call it 50%, be really conservative, call it 70%, be extremely conservative, it's still gigawatt hours a year of useful energy that's available for second life energy storage.
Do you have questions about how potential policy changes or tariff adjustments could impact development and procurement plans? ANSA can help companies move fast, stay informed, and make better procurement decisions. With in-depth supplier relationships and 20-plus years of industry experience, ANSA's team can help buyers rapidly execute procurement strategies that hedge against trade and policy risk. ANSA offers the industry's most comprehensive platform for supplier, product, pricing, and availability data, plus several gigawatts of U.S. inventory ready for purchase. Whether you are looking to evaluate risk exposure, move quickly on inventory, or simply gain better visibility into market options, ANSA is here to help. Learn more at go.ansarenewables.com/latitude.
Catalyst is brought to you by Energy Hub. Energy Hub helps utilities build next-generation virtual power plants that unlock reliable flexibility at every level of the grid. The Energy Hub platform takes the guesswork out of balancing energy supply and demand. It uses machine learning to control customer-owned distributed energy resources like EVs, home batteries, and smart thermostats to precisely shape load profiles for grid flexibility and reliability. As the industry leader, Energy Hub helps more than 80 utilities manage 1.7 million devices, more than any other edge DERMS on the market. Click the link in the show notes to learn more or go to energyhub.com. Catalyst is brought to you by Antenna Group, the OGs of PR and marketing for climate tech. Is your brand a leader or challenger? Are you looking to win the hearts and minds of customers, partners, or investors? If you're a startup, investor, enterprise, or innovation ecosystem that's helping drive climate's age of adoption, Antenna Group is ready to power your impact. Visit antennagroup.com to learn more.
Do you think that assuming that these economics all continue to hold, does it end up being that for Redwood, where you get a heterogeneous stream of incoming end-of-life batteries, and then you have these two different places you can send them, does it mostly end up being that the EV batteries primarily get deployed as second life assets on the grid, and the non-EV batteries all get sent to material recycling? Like, is that sort of where we land here eventually?
I hesitate to commit to that because I have this constitutional distaste for throwing anything away that still has useful life left in it. We're starting with what is easiest and most sensible, which is full EV packs. Will we ever get to old toothbrushes for grid scale energy storage? I really doubt it. That seems unlikely to happen. But somewhere in between, I think there's probably a happy medium. Maybe it would make sense to repurpose big power banks, kilowatt hour scale power banks in this kind of application. That's a ways away. I think the other thing that's important to look at is just the sheer manufacturing volume. Like, look at the front end of the pipe. I think it's something like 80% of the energy storage is going into EV. So that's where most of the gigawatt hours are going to come out, which is really good for grid storage because those are the packs that are going to be easiest to redeploy. Those are the most robustly engineered packs that have a ton of useful life left in them.
Speaking of which, from a chemistry perspective, as we mentioned, right, what you're recycling now are mostly NMC batteries because they're 10 years old. As we look forward, we'll start to see LFP EV batteries start to get recycled as well. Is there any meaningful difference from your perspective, either in the economic calculus of like what you can get out of that battery at end of life, or in the technical process you have to run through between different chemistries or among different chemistries?
I'll start with the technical process. We're totally agnostic to chemistry type. So because of the power electronics that we've developed, we can really easily integrate low capacity, high capacity, high nickel, LFP, new, old, low voltage, high voltage packs, whatever it is. We're ready to plug it in. From an economic perspective, the economics are different for LFP, but they still solve. The metals values are lower. The cycle life is different. The degradation is different. The energy value is different, but it still makes sense to deploy them on the grid used LFP packs.
So the one thing we haven't talked about is like what applications on the grid make sense for these second life energy storage assets. How do you think about that? Should we think about it just like the exact same thing as a new LFP pack that we're deploying on the grid, or is there a distinction?
There's a distinction. We can certainly play in the 2-hour, 4-hour markets with repurposed EV packs, second life packs. Where we see them really starting to shine, though, is in the longer duration markets. So 4-hour, 8-hour, maybe longer, maybe 20-hour. And that's because when you are using these packs at much lower than their rated current, when you're discharging them more slowly, you can tolerate more than you could at the high C rates. So an impedance imbalance, things like that become less relevant. And so we find it makes more sense to deploy in places with high energy and somewhat lower power than what you might see typically.
When you say you could tolerate more, what does that mean technically?
Yeah, so like what does capacity fade look like in an EV pack, right? One of the things is cell imbalance. You have 100 battery cells stacked up in series. One of them gets a little old, gets a little weak. And so when you try to accelerate onto the freeway, that cell has to be limited. We have to protect the weakest cell in the link. And so you can't get the full power out. You can't get the full capacity out, in fact, at those discharge rates. But when you're discharging it more slowly, in some sense, that weakness is much less relevant to the performance of the pack.
Which would be true of not just Second Life packs, right? That's true in general. If you operate at a lower C rate, it's easier to manage, right? So what's distinct here is that you probably have more cells that are tired, so to speak, at end of life than at the beginning of life. But the reason why we don't generally do 20-hour lithium ion de novo projects on the grid is an economic one, right? It's just cost scale kind of linearly
Cost of energy.
with duration. Is that not true with these Second Life packs, or is it just that it is so cheap you can afford it?
That's probably the best way to think about it. We can go toe-to-toe with brand new lithium-ion packs in the 4-hour market and the 2-hour market using Second Life packs. But where it really starts to shine and where you really start to see, I think, just a beautiful reuse is where you have way more energy. And I think you framed it well, which is it's because the cost of that energy is lower.
Right. It's not a fundamentally different equation. It's just that it's cheap enough. You can stack a bunch of things to make a 8-hour, 12-hour system, whatever it is.
Yeah. If you are able to, integrate all of these disparate pack types, which again, I don't want to trivialize that. It's some engineering work to get all these things to play nicely together. Then there's a ton of useful life left to be recovered.
Okay, so this is fun and exciting. I guess the higher level question is like, at what point does it matter from a, bigger picture, this will impact the market perspective? So talk to me a little bit about volume. I mean, you mentioned 5 gigawatt hours total end of life batteries coming off of EVs in the United States. But from a Redwood perspective, like how much can you expect to refurbish and turn into ESS batteries in the near term?
We think we can refurbish and deploy gigawatt hours, low single-digit gigawatt hours this year, next year. It's really interesting to me that this is the first moment where this thing that has always made some philosophical sense is now starting to be something that we can have impact with in the world. We can actually deploy and help to stabilize the grid.
All right, Colin, this was fun. I'm excited to see some Second Life batteries operating on the grid, but appreciate your time.
My pleasure.
Colin Campbell is the CTO of Redwood Materials. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. This episode was produced by Daniel Waldorf. Mixing and theme song by Sean Marquand. Stephen Lacey is our executive editor. I'm Shail Khan, and this is Catalyst.